My name is Moulay Akhloufi. I am the head of the Perception, Robotics and Intelligent Machine Research Group. I will talk a little bit about what we do at Prime. We are mainly interested in artificial intelligence. We work mainly in the applied projects, dealing with what you see here in the first presentation: deep learning, computer vision, robotics, high-performance computing. And I will show you some examples. I don't have enough time to show all what we do, but at least you can have an idea about the project we are doing right now. So about Prime. Prime is for Perception, Robotics and Intelligent Machine. We are a research group at Université de Moncton in Moncton, New Brunswick. And our main focus is applied and industrial research in artificial intelligence. And we do, of course, technology transfer with IP transfer to the companies that want to commercialize what we develop in our research group. Currently, we have more than 80% of the project with the industry. Across Canada, from sea to sea, we have companies working with us in Newfoundland and Labrador, and also in British Columbia, and some international partners in France and Chile, for example. So the areas of expertise and the area of projects we have at Prime are in the machine learning side. We work in deep learning, big data analytics, natural language processing, and AI at the edge for smart sensing and IoT. I will not talk today about NLP project, but one of the projects we did with a company located in British Columbia called Two Hat Security is about detecting toxic contents online. The idea is to detect hatred, cyberbullying, etc., automatically in order to moderate the social media, for example. We have another project with them that deals with images to detect nudity in some sites where you are not supposed to have nudity, and to detect child pornography. We have some computer vision project dealing with medical imaging, biometrics, and also industrial vision. I will talk about the medical area in this today. And we have projects also in robotics dealing with the unmanned aerial systems like UAV and UGV, autonomous navigation, and industrial robotics. I am showing here one about industrial robotics. We are building this system with the company called Pathway to Innovation here, located here in New Brunswick. And the idea is to build a machine that can process lobsters. So we are using 3D computer vision and the deep learning to detect important features of the lobster, so it can be cut and processed for commercialization. I will not talk more about this project today, but we will have probably an opportunity in the future to talk in more details about it. So the applications area are various. We have projects in manufacturing, food, wood, etc. We have in the fintech industry, like insurance, for example. We are working with a large insurance company to evaluate the risk of persons that ask for life insurance, for example. And we have some project in project management, like, for example, if you have a team, and you have a project, what people you will put together that can be the most efficient in doing specific tasks. We developed this project with the company here in Moncton. And we have other projects in telecommunications with a company located in Montreal. It's a large company and an international company. In defense and security, I will talk a little bit about some of the projects we have done. And the healthcare, I will show some of the examples we have done in medical imaging, but we have also some project dealing with genomics and proteomics. The idea is to combine the multiple omics to predict cancer, for example. And in the future, we want to deal also about the efficiency of drugs. For example, if you have specific cancer and you have specific genetic profile, how the reaction will be to specific drugs, for example. Can these drugs be efficient for this person or not? So we will have a kind of personalized and precision medicine in the future, and we are working with the Atlantic Cancer Research Institute in this project. So for today, we'll be presenting about security and defense, some of the applications. And I will start with this project we have done with the Department of National Defense of Canada. It was funded by IDEA projects from Defense Canada, and the idea was to detect small objects from aerial images. So here, for example, we are using deep learning for super resolution. We optimized the architecture to be able to detect very small objects and keep the structure of these objects. So these images show you, for example, if you zoom virtually in an image, you cannot locate that object. However, if you develop new techniques such as the ones we have developed in the deep learning area, we are able to zoom and keep the structure of this object. You can see here, for example, with the classical techniques, we have almost lost this object because of the blurring and the smoothing of the image. And we have developed a deep network which is capable to detect, super resolve the image while still keeping the structure of very small object of interest. And you can see here the ground truth. We have this vehicle, and we can locate it with the technique we have developed. Of course, we have developed the technique based on deep learning, but we have added some information at different scales to keep this structure. And we are currently working on super resolving the image to up to 256 times the size. So this one was for 64 times the size of the original image, and we are increasing that size to have the object of interest, but also to recognize, to classify the object. This is just one of the image I showed you here, but in some cases we are interested not just detecting the small object, but categorizing or classifying those objects, and we have done that type of classification in this type of projects. Another project we have done deals with GPS denied navigation. So here we have UAVs that can lose their GPS signal intentionally or unintentionally, and the objective is to be able to come back to safer area even if their GPS is not is useless, for example. And this is an area of interest right now. We want to be able, even if the GPS signal was jammed or compromised because someone wants to make sure to take some, let's say, an enemy that wants to take your drone, for example, in some kind of situations, you want to bring your UAV to a safer area. So we have developed a computer vision techniques that can extract some important features in different type of images. And in the upper part, you can see that here we have, I will show you the video in 1 minute. It shows that we extract some features in our way from position A to position B. And in this case, we simulate that we have lost the GPS and we go back to position A. So we are using those features to locate our position using images to go to the safer area. And you can see here the system working in a real-world scenario. These images were taken near Moncton. We fly the drone in about 10 kilometers to evaluate the performance of the algorithm. And the algorithms work also with predicting where to look next. For example, if you have a position, you want to limit where to look to decide of your next position. This limits the number of frames used for prediction. In average, we have close to 7 images used for to decide where to go or where to look. And we were able, in average, to get close to our position, to the starting position with 24 meters error over 10 kilometers, which is very good precision. And we don't keep the images because the storage is limited. What we do is we extract some important features, some salient features, and for 10 kilometers, for example, all the features, all the path is compressed in an equivalent of 5 megapixels image, which serves as breadcrumbs, for example, to find our way back. Another project we have done also related to UAV is about a drone chasing other drones, or UAV tracking if you like. And we have developed a reinforcement learning, a deep reinforcement learning technique to track UAVs in real time. So the idea is to use deep learning as a policy to develop a reinforcement learning solution, so a drone can track or can chase another drone in real time. And the idea here is with the reinforcement learning, we want to predict which action to take, at what direction we want to go. And we added also what we call search area proposal. The idea is to predict where to move next, and combining this information, we can be more robust in predicting the next position of the UAV and track it efficiently. And you can say here in a video, this video shows the tracking working outdoor. So the first drone is maneuvered by a human, and the picture that you are seeing here is the drone that is tracking these other drone. So the idea is to keep it and not to lose it, to keep track of this drone and to detect it in real time by using reinforcement learning and search area proposal, including prediction. Of course, we cannot test at large scale. So what we did is we tested the same type of algorithms using a simulator. In this case, it's AirSim, and AirSim with Africa as an environment. So the idea is to tracking drones in an African environment. Using this kind of solutions, and it's working very well. In this kind of scenario, we have also not only the visible camera images, but also near infrared images. Another project related to security is Wildland Fires. If you have watched the news lately, you have seen a lot of forest fires in Australia, for example, in California, and with climate change, it is predicted that we will have more and more fires. We are working in this project with our colleagues in France, in the University of Corsica, and the idea here is to use stereo vision, working a multimodal stereo vision system, working the visible and the near infrared spectrum, and extract the shape of the fire to build an approximate 3D model. And with this approximate 3D model, you can extract a lot of measures that can be input to the mathematical model of fire propagation. So, for example, instead of fighting the fire locally, you can predict where the fire will be in 1 hour and send your firefighters to fight strategically against the fires. And to get this kind of result, we need to have very good segmentation. In this case, we have one of the best in this type of segmenting this type of images in uncontrolled environment. As you can see, these are images of real forest fires. And we have developed a deep learning model which is capable of having an accuracy of more than 97% and F1 score of 91%, which gives a very good shape of the fire. And we can, for example, with 2 cameras, use these shapes to extract salient feature or salient points that with stereo, we can build an approximate model of the fire. Keep in mind that we are dealing with fire, so we don't need a very high precision, but we need to approximate the shape of the fire. And with this approximation, we can detect or we can input this information to the fire propagation model. And of course, we have used this with aerial images. Our objective is to use UAVs to fight against forest fires. And you can see here aerial images captured by, in this case, a helicopter. We are able to detect very efficiently the areas where the fire is present. The other topic that I will talk today is medical imaging. And in medical imaging, we have different projects. I will show here two of them. The first one is about AIDS diseases, and we are interested in the causes of the main causes of blindness in developed world, mainly the AMD, age-related macular degeneration, the diabetic retinopathy, and the glaucoma. We have developed two solutions, one for AMD and one for diabetic retinopathy, and we are working right now for glaucoma. And I will show you the result. In fact, the idea is instead of picking up the different positions of the signs that can tell you if there is a disease or not, we are using an end-to-end solution that takes the image, outputs the grade of the disease, but also, which is very important, outputs the area where the signs of the disease are present. In this case, we are talking about explainability, so we highlight the area where the signs of the disease are present, and for example, an ophthalmologist can have a look to that and confirm the diagnosis. So to summarize the results for diabetic retinopathy, we are using fundus images. We have 4 grades, and we obtain an area under curve, which is a metric used for to evaluate deep learning or machine learning models in the case, for example, of medical images to get the compromise between true positive, false positive, true negatives, and false negatives. So area under curve is a very good metrics for that. And we have a 98.6% tested on more than 80,000 images with a specificity of 97% and sensitivity of 95.8%. And for ophthalmologists that need to detect or to classify if you have a referable diabetic retinopathy or the vision-threatening diabetic retinopathy, we have in the first case for RDR an area under curve of 98.4%, and for the vision-threatening case a 99% area under curve performance for this detection. And in my left, you can see that we can precisely locate the signs of the disease, and this is very important because it can serve as a tool to help physicians in their diagnosis. For the DME and the AMD, we use OCT, optical coherence tomography. Optical coherence tomography takes the depth of the retina, so you have the volume of the retina, and we developed a solution that is capable from these images to detect which type of disease we have. If we have a choroidal neovascularization, diabetic macular edema, drusen, or we are in a normal case. And to summarize the result here, we have these results for AMD and DME, including the drusen and the choroidal neovascularization using optical coherence tomography. We have an area under curve of 99.8% in detecting these diseases, tested on more than 80,000 images, a specificity of 98.7% and a sensitivity of 98.4%, which is a very high result in this type of situation of problems. And similarly to the other approach, we detect or we locate the signs of the disease efficiently. So we have the explainability model that can help the physicians diagnose the disease. We are deploying this solution so it can be used by health professionals. We're talking with some partners that will start beta testing our solution because the results are seems to be interesting for them and they want to test it. So it will be deployed in December and available for health professional and the researchers that want to test the solution online. We also work on AI for radiology, mainly for chest X-rays. And you can see here, there is different diseases on these images, and we want to detect these diseases robustly or as precise as possible. So we have worked with a data set coming from Stanford with more than 200,000 images with 14 observations, different diseases. And we want to use a deep learning and end-to-end model to detect these diseases. And currently, we have an average performance with an area under curve of 96% if we take all these diseases. And for some of the diseases like pleural effusion, for example, or cardiomegaly, where we have very high results. The lowest results are for example, pneumothorax, where we have some results close to 94%. So we are still working on this solution to make it more robust and to increase the performance of the detection of the diseases, including explainability, like we have did for the eyes and the eye diseases. And we have adapted this solution for CX-ray to detecting COVID-19 using X-rays. We are working on this project with the hospital in Ottawa with very interesting results. We have two scenarios right now we are testing with them. One that detects three classes, normal, other, pneumonia, and COVID. We have sensitivity of 95% and specificity of 96% with explainability, locating the area where the disease is present. And we also tested COVID as pneumonia, so combining all in the same class compared to normal, and this increases the sensitivity to 98% with a specificity of 92%. And we are testing right now this solution with the hospital and the Research Institute of Montfort in Ottawa. We have also deployed this solution online so people can use it. And it's right now we see that many people use it from worldwide. So it's there, it's free for everybody to use. And of course, with our partners, we give some access, some special access to the recent models or the models we are improving over time. So this is my presentation for what some example of what we are doing at the Perception Robotics and Intelligent Machines Research Group here in Moncton. So feel free if you have questions for me. Thank you.
Zaid has asked, what data pipeline technologies do you use for the real-time feeds of data?
In what project are we talking about? Because in fact, we work mainly with data sets that are available or that we capture ourselves. Of course, when the data sets are available, it's cool. They are labeled and they are segmented and everything. When we collect our own data, like the example for UAVs, we had to collect because there is no data sets available with UAVs chasing other UAVs in real life situations. We had to do it ourselves. And for GPS denied navigation, we did the test outdoor ourselves. So we captured the data. We train our models. We are working mainly with deep learning models, and we optimize. As I said, we work also in AI at the edge. So our people know how to optimize the code to make it run in an embedded system, for example, at the edge, which help, for example, to improve the processing time, even if you have an embedded system. I don't know if this answers the question.
I would say so, yes. Excellent question, Zaid, and great response there, Moulay. Jumping on to Andrew. Andrew has asked, do you use Kalman filters for the drone tracking algorithms in connection with reinforcement learning? And is the algorithm able to ID different objects?
Yeah, that's a good question. In fact, we don't use Kalman filter because Kalman filter is expects that the motion is linear, which is not always the case. Specifically, like you said, for example, drone chasing drone, you have a person trying to escape the other drone, so the motion can be nonlinear. So we have based our solution on particle filters, and particle filters enable to take into account the nonlinearity of the motion. So that's the type of algorithm we use. And of course, we combine that with the reinforcement learning and convolutional neural networks to train our model and to improve the performance.
Great. We'll jump to Wilco now. Wilco has asked, which machine learning stack do you use to build these systems? Mostly open source or a lot of internal developed software and algorithms?
Yeah, we have, of course, we base our development on two main libraries, TensorFlow and PyTorch, like everybody. I mean, everybody is using that. And for optimization, we use TensorRT, for example, from NVIDIA, specifically when we are working with NVIDIA platforms. But we have, of course, when we develop our some specific algorithms or some specific recipes that improve the performance in some cases, we develop our own software. But this, I would say that this is probably 20% of the job, because in general, what you do, you use what you have, like TensorFlow and PyTorch. And when the solution doesn't work as you like, then you write your own code. And the pieces, I will say probably it's 20% of the project.
Great. We'll jump to Andrew now. Andrew has asked, is Prime a corporation or only a research group for enrolled students at the University of Moncton?
Yeah, Prime right now is a research group, and it will become an AI research center soon. We have the budget, everything, but with COVID, everything was delayed. With the research center, we will be bigger. And just to say, probably it's the good time to say it. We are hiring. And we are hiring a lot. I mean, there's a lot of position, and probably you have seen that these projects are fun. We have a lot of fun doing this project. The students are happy, the research professionals are happy, and we don't. I don't say we are working. We are almost having fun, even when we develop some industrial project. It's really, I mean, you enjoy what you are doing when you work in deep learning, machine learning, and this kind of things. So we are recruiting. So if there is postdoc at master's, PhD levels, at every research professional, and what we are developing right now are spin-off, because in general, what we do is we transfer the technology to our partners, industrial partners, but we are working specifically for the medical area in some spin-ups that will be created, because we have some companies interested in creating spin-ups with us related to these kind of technologies that we have developed.
Is there some significant processing power on the drones themselves?
No, in fact, that's a very interesting question. So just to, of course, as you know, deep learning, you need to train in a good performance computers. We built our own servers. We use Compute Canada for some of the research project, but we have built our own server ourselves with the multiple gaming cards, like the RTX 2080 Ti that we use. We have 8 of them in parallel working in our server, and we are developing a new one with the new technology, the Ampere ones that were developed recently by NVIDIA. And we are working on getting DGX A102, because we need a lot of processing power to train. This is for training. For inference, we optimize the processing to make it real time. As I said, for example, when you are working with NVIDIA, you can use TensorRT, and you will be working not just with Python, but of course, training, everything is done with Python. And once you have your model, if you want real-time performance, you will have to jump to C++, because probably with Python, you cannot achieve this performance. So we optimize depending on the platform that we are using. Since the majority of the platforms are NVIDIA based, I would say the keyword is TensorRT. It works very well for us, and that's the kind of things we are using right now.
Lou has asked, in the first example where you were detecting an object in 64K, is the detection done in real time? How much detail would you present when you implemented a 256K resolution, and what distances are involved in the between the camera source and the object being detected?
Yeah, I'll start with the last one. We don't have the estimates, because we use data sets that don't have these estimates about the altitude, for example. But we can see that the the objects are very small. Now, the models we have developed with the 64X is the most important things to keep in mind is that we are working with different type of images. Probably you can browse and you can see that we can achieve a very high performance with super resolution if we are, for example, working with faces, because it's just one object, it's a large object in the image, and it's easy to do. You will lose some precision near the mouth, for example, because we have worked on this type of solutions to build face recognition at a distance, and it works very well. We have very good performance when we use super resolution with that. But the idea here is to increase virtually the size of the object while still keeping enough information to classify the object. Okay, I showed some objects in the ground, but the most challenging aspect, and probably since it's not classified, this project we will publish a paper on that. The most challenging part is in the sea. When you have boats and you have a lot of water and you want to increase the resolution while keeping enough features to recognize what type of boat it is. That's a challenging task, and we have built a deep learning architecture, a convolutional architecture based on GANs, generative adversarial networks, but that takes into account multi-scale to improve the quality of the structures we want to keep. But to answer the question, we want to keep enough structures to recognize the object.
Regarding the wildland application, can or will you be able to detect the source, i.e. the ignition of the source of the fire based upon the type of flame and surrounding area?
Yeah, we don't deal with that. In fact, our objective is to have enough data to input to the mathematical model that predicts the propagation of the fire. And to understand the objective is, I will put it simple. The idea is when you have fire, instead of trying to fight against the fire locally, which is just running after the fire, what you will do, you will accept that the fire will burn some area, but if you can predict based on this information where the fire will be spreading in 1 hour or 2 hours, you can send your firefighters to some location that so they can put some trenches and block the advancement of the fire. That's one of the strategies we can use, or we can put some retardant in some specific area so the fire can slow down and we can fight efficiently against it. So that's the idea beyond this solution. I don't think we can, we can put a system that can detect the fire, since we detect it with a very good accuracy, and that detects when the fire starts. But you will need probably a lot of cameras that monitor a large area. And this is something interesting because it can be complementary to fighting the fire. Early detection of the fire is important too.
Eric has asked, for some examples, you measured your classifier using AUC. For some other examples, you used F1 scores. Why did you use different criteria for different examples? Why not use the same criterion for all examples?
You cannot use, in machine learning, deep learning, you have different metrics, and different metrics gives you specific information. For example, if I am just classifying an object, accuracy can be enough. But if you are, for example, for the segmentation, you need to know how many pixels you have detected as fire and how many you have lost. And in this case, F1 score is the best one to do this job. For medical applications, you have a compromise. You don't want to have a lot of false positive nor false negatives, right? And in this case, area under curve is one of the best metrics. We can also use F1 score, but area under curve is widely used in the healthcare applications because it gives you a good idea about the performance of your detection and the compromise in good detection and false detections.